If light suddenly slowed down to the speed of sound, you'd still see the sun shining for 8 minutes. But when the new, slower light finally reached Earth, you wouldn't recognize the universe anymore. And honestly, you probably wouldn't survive long enough to care. Light is fast, really fast. It travels at 300,000 kilometers per second. That's so fast it can circle the Earth 7.5 times in 1 second. And we kind of take that for granted, right? Light just does its thing. It bounces off objects, hits our eyes, and we see stuff. The speed of light is built into every aspect of how the universe works. But what if it wasn't? What if the speed of light suddenly changed? Not disappeared, not got brighter or dimmer, just slowed down. Let's say it dropped to the speed of sound, about 343 meters per second. That's 1,000,000 times slower than it currently is. Today, we're going to walk through what would actually happen if the speed of light suddenly decreased. And I'm telling you right now, this breaks everything. Physics, chemistry, reality itself, all of it falls apart in ways that are both fascinating and absolutely terrifying. Here's the core problem with slowing down light. The speed of light isn't just a random number, it's fundamental to how the universe operates. Einstein's famous equation, E equals mc squared, has the speed of light in it. The electromagnetic force depends on it. Atoms are held together by forces that rely on the speed of light being exactly what it is. Change the speed of light, and you don't just change how fast photons move. You change the strength of electromagnetism. You change how atoms bond. You change chemistry. You change energy levels. You potentially change nuclear forces. In other words, you break reality. So the challenge here isn't just, what would it look like if light moved slower? The challenge is, could anything even exist if light moved slower? And the answer to that is, probably not, at least not in any form we'd recognize. But let's walk through it anyway, because the thought experiment is wild. Okay, let's set up the scenario. Right now, at this exact moment, the speed of light changes. It drops from 300,000 kilometers per second down to 343 meters per second, the speed of sound. The first thing you need to understand is that this change doesn't affect light that's already traveling. Light that left the sun 8 minutes ago is still moving at the old speed. It's going to reach Earth just fine. But new light, light being emitted by the sun right now, is moving at the new, slower speed. The sun is 150 million kilometers away. At 343 meters per second, light would take about 13.8 years to reach Earth. So for the next 8 minutes, everything would look normal. The sun would shine, the sky would be bright, you'd have no idea anything was wrong. But after 8 minutes, the old light runs out. And then, darkness. Not forever, just for 13.8 years until the new, slower light from the sun finally arrives. Except you wouldn't be around to see it, because by that point, Earth would be frozen solid and you'd be very dead. But let's ignore the cold for a second. Let's assume you could somehow survive without sunlight. What would the universe look like when light is that slow? Here's something wild. If light traveled at the speed of sound, you could see it moving. Right now, light is so fast that it seems instantaneous. You flip a switch, the room lights up, no delay. But that's only because light moves at 300,000 kilometers per second. It crosses the room faster than your brain can process. But at 343 meters per second, you'd see the delay. If you turned on a flashlight, the light wouldn't instantly illuminate what you're pointing at. You'd see a beam slowly creeping forward like a glowing stick extending from the flashlight. If you pointed it at something 100 meters away, it would take almost a full second for the light to get there. Shadows would work differently too. If someone walked in front of a light source, you wouldn't see their shadow immediately. You'd see the light that was already traveling keep going, and then a moment later the shadow would appear and start spreading outward at 343 meters per second. It would be bizarre, disorienting, like living in a universe where cause and effect were constantly out of sync. And it gets weirder. Light isn't just one thing, it's a spectrum. Different wavelengths of light create different colors. Red light has a longer wavelength, blue light has a shorter wavelength. And wavelength is directly connected to frequency. The speed of light equals wavelength times frequency. It's a basic equation. If you slow down light but keep the frequency the same, the wavelength has to get shorter, a lot shorter. Red light, which normally has a wavelength of about 700 nanometers, would now have a wavelength of, let me do the math, about 0.00007 nanometers. That's smaller than an atom. But here's the thing. Atoms interact with light based on wavelength. The reason plants are green is because chlorophyll absorbs red and blue light but reflects red. The reason blood is red is because hemoglobin absorbs other colors but reflects red. If all the wavelengths suddenly got 1,000,000 times smaller, nothing would look the way it's supposed to look. Everything would be the wrong color, or maybe no color at all, because the wavelengths would be so small they'd interact with matter in completely different ways. Actually, let's be honest, at that scale, light might not even interact with atoms the way it normally does. It might just pass through everything like a ghost. Or it might get absorbed instantly and converted to heat. Either way, the universe would look nothing like it does now. Okay, let's talk about the real problem, the one that makes this whole scenario impossible. Atoms are held together by the electromagnetic force. Electrons orbit the nucleus because they're attracted to the protons inside, and the strength of that attraction is determined by a fundamental constant called the fine structure constant. The fine structure constant depends on the speed of light. If you change the speed of light, you change the fine structure constant. And if you change the fine structure constant, you change how strong electromagnetism is. Slow down light by a factor of 1,000,000, and electromagnetism gets 1,000,000 times stronger, or weaker. Depends on how you model it, but either way, atoms don't work anymore. If electromagnetism gets stronger, electrons would spiral into the nucleus. Atoms would collapse. Everything would turn into a dense ball of neutrons, not gradually, instantly. If electromagnetism gets weaker, electrons would fly away from the nucleus. Atoms would come apart. Matter would just disintegrate into loose particles floating around. Either way, you're dead, instantly. Along with the entire planet, along with the sun, along with every star, planet, and chunk of matter in the universe, because everything is made of atoms, and if atoms can't exist, nothing can exist. Let's talk about E equals mc squared for a second. This equation tells us how much energy is contained in mass. Take your mass, multiply it by the speed of light squared, and you get the energy equivalent. For a 1 kilogram object, that's 1 times 300,000 squared, which equals 90 quadrillion joules. That's 90 quadrillion joules, a massive amount of energy locked up in a small amount of mass. But if the speed of light dropped to 343 meters per second, that same 1 kilogram object would contain 1 times 343 squared, which equals 117,649 joules. That's about the energy in a cup of gasoline, compared to 90 quadrillion joules. What does that mean? It means all the energy stored in mass would suddenly disappear or convert into something else, or reality would just have a hard time figuring out what to do with the inconsistency and everything would explode or collapse or both. Nuclear reactions depend on E equals mc squared. The sun produces energy by converting mass into energy through fusion. That process releases energy based on the speed of light. If the speed of light dropped, the energy output of the sun would drop. Not just dim, it would basically stop. The sun would go out almost immediately because the fusion reactions wouldn't release enough energy to sustain themselves. And stars across the universe would do the same thing. Every star, all at once, just off. The universe would go dark, not because light stopped existing, but because the sources of light stopped working. Here's something people don't think about. The speed of light is connected to time. According to relativity, space and time are linked. They're part of a single structure called space-time, and the speed of light is the conversion factor between space and time. When you move through space, you move through time more slowly. That's time dilation. It happens at high speeds, close to the speed of light. But if the speed of light dropped to 343 meters per second, then moving at everyday speeds would cause massive time dilation. A car going 100 kilometers per hour would be moving at about 28 meters per second. That's about 8% of the new speed of light. At that velocity, time would noticeably slow down for the people in the car compared to people standing still. Not by a huge amount, but enough that clocks would drift. GPS satellites wouldn't work. Hell, regular clocks wouldn't stay synchronized. And if you got in a plane going 900 kilometers per hour, which is about 250 meters per second, you'd be traveling at 73% of the speed of light. Time would slow down so much that you'd experience serious relativistic effects. You'd age slower than people on the ground, your watch would run slower. From your perspective, distances would contract. A flight across the country would seem shorter because space itself would appear compressed. It would be absolute chaos. The laws of physics that we rely on for navigation, communication, and basic timekeeping would all break down. Here's the really messed up part. The speed of light isn't just about light. It's the speed of causality. It's the maximum speed at which information can travel, at which cause and effect can propagate. If you do something over here, the effect of that action can't reach over there faster than the speed of light. That's a fundamental rule of the universe. But if the speed of light dropped to 343 meters per second, then causality would propagate at 343 meters per second. That means if you clapped your hands, the sound would reach someone 100 meters away at the same time as the information that you clapped, because sound travels at the speed of causality now. Except that doesn't make sense, because sound is a physical wave that travels through air, and causality is different. It's not a wave, it's the structure of space-time itself. This is where the thought experiment breaks down completely, because slowing down the speed of light doesn't just change how fast photons move, it changes the fundamental structure of reality in ways that are incompatible with how matter and energy work. You can't just dial down the speed of light and expect everything else to stay the same. The universe is an interconnected system. Change one fundamental constant, and everything else has to change to compensate. And most of those changes would make life impossible. Let's pretend, for the sake of argument, that somehow atoms didn't fall apart and people could survive in this new, slow light universe. Communication would be a disaster. Right now, when you make a phone call, the signal travels at the speed of light through fiber optic cables or as radio waves through the air. It's so fast that there's no noticeable delay, even if you're calling someone on the other side of the planet. But if light traveled at 343 meters per second, phone calls would have lag, massive lag. Calling someone 100 kilometers away would have a delay of about 5 minutes each way. So you'd say something, wait 5 minutes, they'd hear it, they'd respond, and you'd hear their response 5 minutes later. Every conversation would take 10 minutes per exchange. The internet wouldn't work, streaming wouldn't work, GPS definitely wouldn't work. Satellites would be useless because the signals would take hours to go up and come back down. And forget about space exploration. If we sent a signal to a Mars rover, it would take decades to get there at the new speed of light. Humanity would be isolated, cut off. Every person, every city, every country would be living in their own little bubble of causality, only slowly able to interact with the bubbles around them. It would be like going back to the age before telecommunications, except worse, because we'd remember how fast things used to be. Here's the thing that really puts this into perspective. The speed of light isn't just a speed limit. It's the framework of reality. It's the skeleton that holds the universe together. Change it, and everything collapses. Atoms fall apart. Energy disappears. Stars go out. Time goes haywire. Causality breaks. The universe as we know it just stops working. We think of light as this thing that moves, photons traveling from point A to point B, but it's so much more than that. The speed of light determines the strength of forces. It sets the scale of energy. It defines the relationship between space and time. If light slowed down, we wouldn't just see the world differently. We wouldn't see the world at all, because the world wouldn't exist. Not in any form we'd recognize, maybe not in any form at all. And that's what makes this thought experiment so fascinating and so terrifying. It shows us how delicate the universe is, how perfectly balanced the constants of nature have to be for anything to exist. We live in a universe where the speed of light is 300,000 kilometers per second, and if it were anything else, even a little bit different, we wouldn't be here to wonder about it. So, let's wrap this up. If the speed of light suddenly slowed down to the speed of sound, here's what would happen. For 8 minutes, we'd still see the old light from the sun. Everything would look normal. But then the old light would run out, and we'd be plunged into darkness for 13.8 years until the new, slower light arrived. Except we wouldn't make it that long.